Alright, so today we're going to talk about section 5.2, dealing with certain types of points of concurrency in a triangle. Your circumcenter, your incenter, and your centroid. We'll also discuss a fourth type, the orthocenter. Now your circumcenter, incenter, these are both special points of concurrency. So circumcenter is when your perpendicular bisectors of a triangle intersect inside the triangle, whereas the incenter is your point of concurrency of the angle bisectors of a triangle. So these two bisectors will meet at a single point. Circumcenter for the perpendicular bisectors, incenter for the angle bisectors. They have a certain property which we will also discuss when that happens. Now, in addition, we also have the median, which we explored last time in last chapter. This is a segment going from the vertex of a triangle to the midpoint of the opposite side. And, like our perpendicular bisectors and angle bisectors, the median has a point of concurrency. This is called the centroid. This is where all the medians will meet. And it also has its own property as well. And then finally, the last two pair, the altitude. This is your perpendicular segment from the vertex of a triangle to the opposite side. And then the orthocenter is the point of concurrency of the altitudes of the triangle. So we're going to discuss these four different points of concurrency and what their relationships are with the different segments and how we can solve different problems using this relationship. So your circumcenter theorem says your perpendicular bisector triangle all intersect at your circumcenter such that that is equidistant from the vertices of the triangle. So point G is our circumcenter for this triangle. This guy right here. DG, EG, and FG are all the perpendicular bisectors of the triangle. They don't necessarily have to go through the vertex. So don't assume CD is one line. It's not. CG is one line and it's kind of like an angle off to DG. It just appears that way because the triangle is pretty equilateral. So our three perpendicular bisectors are not going to be the same lengths. They're not equal. However, distance from that circumcenter to the vertex, that distance is equal for all these. And the reason why is if you consider this your perpendicular bisector right here, ignoring everything else, you notice perpendicular bisector, equal segments, these two pieces should be the same length. And we use that logic throughout the rest of the problem. Incenter is the same concept with the angle bisectors, now just the opposites. So now these perpendicular segments, these are equidistant from the sides of the triangle. So all these values, DG, EG, and FG are all the same distance, whereas the actual angle bisectors, we don't know anything about their lengths. They're not equal. So if you need help remembering them, it's just the reverse logic. They're just opposites. Perpendicular bisectors, perpendiculars aren't equal, the other lines are. Angle bisectors, the angle bisector lines are not equal, but the perpendicular lines are. It's just reversed. So let's use this to solve some problems. So when you're solving problems like this, you need to identify whether you have perpendicular bisectors or angle bisectors. And in this case, we have perpendicular bisectors. I have no angle bisectors. So if I have the perpendicular bisectors, well, that means that my lines from the vertex to the circumcenter all be equal. So if AG is 12, BG and CG are also going to be 12. The other perpendiculars themselves, we don't know anything about, so even though this is 9, I cannot figure this out. EG and FG are both going to be a no solution case. If I am given the angle bisectors, as in this case, so again, we ask ourselves, which one do we have? As you can see, we do have angle bisectors, and none of the perpendiculars are bisecting, so we have this case. With our angle bisector case, the perpendicular lines themselves are all going to be the same lengths. So DG, EG, and FG are all going to be, in this case, 7. And then the angle bisector lines themselves, we don't know what their values are going to be. They could be 15, but they're probably not going to be. So we just kind of answer, no. We don't know what they are yet. So you just have to remember the differences between the two. And again, if you have to, just kind of like break it down by just ignoring the entire triangle except for your angle bisector situation. And remember that if we have an angle bisector, these two angles are equal, therefore these two segments are equal. Using that same logic telling you the rest of the bisectors. Now in this case, this is getting a little interesting. So we have a perpendicular bisector, angle bisector. Which one do we have? Well, I do have angle bisectors, and I have perpendicular bisectors. I have them both. If I have them both, I can answer everything. AG, BG, and CG are all the same, so these are all 20s. DG, EG, and FG are all the same, so those are all 10s. So if I have both situations, I can answer everything. I can fill the rest of the diagram in based off that. If I have nothing, I don't have any marks for angles, any marks for sides, I don't have any of the situation, I just have some normal triangle, I don't have enough information. This entire thing cannot be figured out. So those are your four possibilities. Either I only give you perpendicular bisectors, I only give you angle bisectors, I give you both, or I give you neither. And you need to be able to recognize the difference between which ones are which. And again, if you have to, going back, for example, perpendicular bisectors, if you erase everything, except for one set of perpendicular bisectors, you'll notice we have our perpendicular bisector. If these two segments are the same, these two segments must be the same. That's AG and CG, and that's how we know they're 12. BG is also going to be 12. Now your centroid theorem, let's deal with medians now. The medians of a triangle will intersect at the centroid that is 2/3 the distance of the length of the median. So there's two different ways to look at that. So this distance right here, AG, will be 2/3 length of the entire median. BG is 2/3 length of its entire median, BF. And CG is 2/3 the entire median, CD. Well, this is 2/3. This other piece has to be 1/3. So another thing you can say is DG is 1/3 of its median, CG, or sorry, CD. EG is 1/3 its median, AE, and FG is 1/3 its median, BF. And then if this is 2/3 and that's 1/3, another way to look at this is CG is double DG, and BG is double GF, and AG is double EG. So if I know one of these pieces, I know the rest of them. So if you're given AG and you want to find AE, you just do AG equals 2/3 AE and solve like that. If you're given AE and you want to solve for EG, use this equation. So you just have to remember it's 2/3 from the vertex to the centroid is the entire median. It's 1/3 from the side to the centroid. Your orthocenter, well, there is no relationship. They have no actual mathematical relationship besides just creating right angles. So if you see only orthocenter problems and you cannot solve it, then you're done. So keep that in mind. So for these examples, I want to use what we just talked about with our medians to solve these problems. So I'm given the median AE, this whole line. I want to find AG. Well, the median, 2/3 of that, is the distance from the vertex to the centroid. So 2/3 of 24 is going to be 16. So AG would be 16. If I'm given BF and I want to find FG, well, BF is the entire median, so I'm going to have to do some fraction times the median. If I want FG, well, that's the smaller piece. So that's 1/3 the median. 1/3 of 30 is 10, so FG is 10. Now I'm given BG, so I'm given a piece of it. If I want to find BF, well, 14 has to be 2/3 of some unknown x, or BF value. So in order to get bigger, I need to multiply this by 3/2. 3/2 times 14 is going to be 21. If I'm given CG, and I want to find the value of DG, the other smaller piece, well, as we saw before, if we're talking about 2/3 and 1/3, this is double that. So if I take half of 26, that'll give me the smaller piece DG, which is 13. And then when we're given the smaller pieces EG and FG, we're either doubling it to get to the other piece, or I'm tripling it to get the entire median. So if EG is 9, and I want to find the entire median AE, I triple 9, and get 27. If I'm given FG, and I want to find the other piece BG, the other smaller piece, we're going to double it. 11 times 2 is 22. And those are really your 6 possibilities. I'm either going to give you the entire median and ask you to find the bigger piece or the smaller piece. If it's the bigger piece, you do 2/3 of the median. If it's the smaller piece, it's 1/3 of it. I can give you the bigger piece of the median and ask you to find the entire length. You're just going to multiply it by 3/2. Or I'm going to ask you to find the smallest piece, which you cut in half. Or I'm going to give you the smaller pieces. You're either going to multiply by 2 to get the other piece of the median, or multiply by 3 to get the entire median. Okay, so that's your relationship with your angle bisectors, perpendicular bisectors, medians, and then altitudes. So next time we're going to talk about different triangle relationships. So I'll see you next time.